Last time we have discussed the top-down parsing approach and the bottom-up parsing approach. From the bottom-up parsing approach, we have discussed the general approach without the use of stack implementation, or without using stack. Now we will discuss in this particular session about the general top-down parsers, which are the LR parsers. And LR parsers use LR grammars. So the LR grammars are the ones, or the type of grammar that are used by LR parsers, and LR parsers are the parser or the syntax analyzer type which follows the bottom-up parsing approach. A given grammar to be LR grammar, it has to be used by LR parsers. So if a grammar that can be parsed by LR grammar examining up to k input symbols on each move, then the resultant grammar is termed as LRK grammars, where k is the set of input symbols. The set of input symbols look ahead. The set of input symbols look ahead. So the very important point here is LR grammars can describe more languages than LL grammars, and LL grammars are the ones that we have discussed in our previous session, which are used by parsers following the top-down parsing approach. So LR grammars are used by parsers following the bottom-up parsing approach. So just as in the case of top-down parsing approach, for the parsers following the top-down parsing approach, we need to construct LL parsing table, LL1 parsing table, or simply LL parsing table. So in the same way, we should also construct parsing tables, LR parsing table for LR parsers, or for the parsers following the bottom-up parsing approach. So here, in order to construct LR parsing table, we can use the three methods, any one of the three methods. So the one is simple LR parsing, The other one is canonical LR parsing, or in short CLR, or the look ahead LR parsing technique, or in short LR parsing technique. So the LR parsing table is created from a given grammar, just as LL1 grammar, or simply LL1 grammar is used for constructing LL1 parsing table. So LR parsing table is constructed from a given grammar using any one of those three methods. So those three methods are just categorized based on their performance, the powerfulness, and the cost of implementation. So the simple LR, which is abbreviated as SLR, is the least powerful but easiest to implement, and the canonical LR, or simply abbreviated as CLR, is the most powerful and the most expensive. So it is implementation cost is too expensive, the most expensive compared to the other two techniques. And the third one is the look ahead, or abbreviated as LLR, is having an intermediate power, and the cost of implementation is also an intermediate, and this works on most programming language grammars. So uh, those are the three techniques. So a grammar that is for which its parsing table, I mean the grammar whose parsing table is constructed using simple LR parsing table, and the parsing table is constructed without any conflict, is considered as SLR grammar. And if it is constructed, its parsing table is constructed using CLR and without conflict, it is considered as CLR. And if it is in LLR, it is considered as LALR grammar. So when we are constructing a parsing table, LR parsing table using SLR, so the resultant table will be SLR parsing table. So for the construction of SLR parsing table, we create LR0 items. LR0 items. So here what we can just summarize here regarding those methods is that in the case of SLR, we construct LR0 items. LR0 items. For the construction of the parsing table, we construct LR0 items, and for this one we create LR1 items, and for this one too we create LR1 items. So the item collection which is required for the construction of those LR tables is different, but the other two, and the CLR and LR, are using LR1 items. So for the construction of SLR parsing table, we construct LR0 items. But the next question that could be raised is, what is basically LR0 item mean? And this SLR0 item is simply a production rule. It is a production rule having dot operator at some position on the right hand side. For example, if we have given a production rule of a given grammar as A drives X, Y, Z, for this particular production rule, we can generate or we can create LR0 items by simply placing dot operator starting from the left end of the right hand side of the production rule until we shift the dot to the right end of the production rule. So every time we are shifting the position of dot operator, we are creating another LR0 item. So for example, the first LR0 item that can be created from this production rule is A drives dot XYZ. This is one. The second one, by shifting the position of dot between X and Y, A drives X dot YZ. This is also another LR0 item. Another item, again placing the dot between Y and Z, X drives XYZ. And lastly, placing the dot to the right end after z, that is another LR0 item. And here keep in mind that for any epsilon production rule, there is only one LR0 item. There will not be two LR0 items like a drivers dot epsilon and a drivers epsilon dot. No, this is not the correct way of generating LR0 items from epsilon production rule. So the only single item that can be generated from epsilon production rule is just simply placing dot on the right side of the production rule. So this is the only LR0 item that can be generated from the epsilon production rule. So before starting generating LR0 items for the construction of SLR parsing table, the first step is augmenting the grammar. So we need to first augment the grammar, and then once we augmented the grammar, we calculate the two functions, closure and goto. So what is grammar augmentation mean? So when we say grammar augmentation, that means adding new introducing new non-terminal that can be used for adding new production rule into the already given production rules of the grammar. For example, if the grammar is G, after the addition of new non-terminal, the resultant grammar becomes grammar G prime. So the very simple way to add new non-terminal is just taking the previous start symbol of the grammar and making it prime to drive the previous start symbol of the grammar. So this is the new production rule that we can consider to add into the given grammar. So after we augmented the grammar, then we go for calculating the two functions, closure and goto. Here, why we need to augment the grammar? We have here a reason for augmenting the grammar. Why? It is because this new production rule that is used to augment the grammar is used to indicate when the parser should stop and announce the acceptance of the input string. So the augmentation is required, or adding new non-terminal and production rule is required to indicate the state or the condition of stopping the parsing process and announcing the acceptance of the given input string. So what closure operation is? The closure operation for a given grammar G is just a way of creating new item by adding production rules whenever we observed non-terminal after dot operator. So after dot operator, if we observed non-terminal like B, we should consider the all B production rules to be inserted into the closure of I. And here what we have to keep in our mind is every time we are adding the production rules of the non-terminal that appeared after dot operator, we should start placing the dot operator from the left end, again. So this is a simple algorithm that shows how we can implement the closure operation on a given input, on a given item I, LR0 item I. So here, for example, if we are given a grammar G, assume this is a grammar G having those production rules: E derives E plus T, E derives T, T derives E times F, T derives F derives in bracket E, F derives ID. So those are the original production rules of the grammar. After augmentation here, we need to augment the grammar first. So how we augmented the grammar is by introducing new non-terminal E prime that can derive the previous start symbol of the grammar E. So this is an augmented grammar. So now applying the closure operation on I. Assume we have this item I having E prime derives E. So applying the closure operation on this I, we have the resultant set having those items. So the first item is E prime derives dot E. We simply add that E prime derives E, just start placing dot at the left end of the production rule on the right hand side. Then the next is, once we added the item, then we look for the non-terminal after the dot symbol. If after dot symbol we have non-terminal, then we go for adding all production rules of the non-terminal appeared after dot operator. So from the original production rules, since the dot operator, after dot operator we have E, we should add all production rules of E. So the two production rules of E that should be added to the closure of I are E prime derives dot E plus T, E derives T. Again, here we have T after dot. Then we go to the original grammar, then add two production rules of T. That's why we have added here the two production rules of T. Again, we have F after dot. Then we need to add the two production rules of F into the closure of I. So this is a set having those different items by applying the closure operation. So here, from those items, we have two categories of items: kernel items and non-kernel items. Then kernel items are the items that include the initial item, that is the item by which we augmented the grammar, and all other items whose dots are not at the left end. For example, T derives T dot star F is kernel item because the dot is not at the left end. So the others having dot at the left end are non-kernel items. For example, T derives dot T times F. For example, F derives dot in bracket E. F T derives dot F. Those are the non-kernel items. And this one, although it is having dot on its left end, it is the one that we have used for augmenting the grammar. That's why it is considered as a kernel item. So the other operation is go to operation. So this go to operation is a way of generating one item from another item. So this go to operation is used to generate one item from another item. And this, how this is expressed, is it is expressed in terms of closure operation. For example, if we have an item a drives alpha dot x beta in a given item I, we can apply this go to of I comma x. We can apply the go to operation on this item I as go to of I comma x. Why this x? Because x is the grammar symbol appeared after dot. So the second argument of go to operation is a grammar symbol that appeared after dot operator. So, and this item is an item that is having this LR0 item. So after this application of this operation, the resultant will be expressed as closure of applying closure operation on a on the given item. So it is will be just similar to apply closure operation on the item by shifting the position of dot. And similarly, after we shifted the position of dot, we should also look for the if there is an internal after dot to add all production rules of the internal appeared after dot operator. So for example, if we have this item I having those production rules, those are the production rules, having the items so if we apply the go to operation on this item I, how we can apply go to of I, the first one after the I, the second argument is E first, because here after dot we have E. So the go to operation of this item I with E, those two items will be considered for calculating the go to operation of I comma E, because here those two items are having E after dot. So we can just express this operation in terms of closure operation as E drives, E prime drives dot E dot, then E drives E dot plus T. So the two items are the only items that will be included or just placed in the result of go to of I comma E. There is no need to add another item into this set, because after dot this is a final item because dot already reached at the right end, and this one is not a final item because it is between E and plus. But here after dot we have plus, and this is terminal symbol. So as it is terminal symbol, there is no production rule that we should include into this set. And the second function operation that can be applied on I is go to I comma T, because here after dot we have T, so on those T production, on E production rule and on T production rule, we can just apply closure. So we can apply closure, so the resultant will be E drives T dot, then T drives T dot star F. So similarly, there is no need to add additional production rule as an item into this set, because after dot we have star, and this is already reached at the right end, so this is final item. For f, go to of I comma f. So here we have only sorry one item that contains f after dot, so we should apply closure operation on only on this item. So here we will have this production rule, which will have dot at the end. And for the next f production rule, that is having terminal symbol opening bracket after dot operator, we have this item, only the single item, but here after the applying closure operation on this item, we have f drivers opening bracket dot e. Then here, as e is non-terminal and appeared after dot, we should go to the original grammar and add all production rules of e. All production rules of e. Here we should add this production rule, and we should add this grammar. So that's why we have e drivers dot e plus t and e drivers dot t, and again we have t after the addition of those two production rules. We have t after dot, then we should add all production rules of t. After dot again we have f, we should add the all production rules of f again. But here what we have to keep in our mind is, whenever we are adding a new a new production rule into the item or into the set, because of the existence of non-terminal after a dot operator, we should start again from the left end. So this is how we can construct, we can apply GOT operation and closure operation for constructing LR0 items. So here to construct SLR parsing table, to construct SLR parsing table, we should augment the grammar, then we should create the canonical LR0 items collection. So this is what you call the canonical LR0 items collection. So here for the given grammar, this I0 is created by applying the closure operation on the first item, as we have seen in the grammar. So the previous example. So this is the we can consider this one as a I0 by applying the closure operation on the closure operation, this one as I0. So this is I0 by applying closure operation on this one. So initial I0 is always created from applying closure operation on the item having the production rule by which we augmented the grammar. Then other items will be derived from the initial item I0 by applying the goto operation. Look, for example, if I0 is created from a closure of the production rule by which we augmented the grammar, then the next I1 should be created from I0 by applying the goto operation. So I1 is derived from I0 by applying goto of I0 comma E. So since we have two production rules, the first two production rules with non-terminal E after dot operator, so those two production rules should be added to I1. So by shifting the dot operator, so when we are creating a new item from another item, we should shift the position of dot, and whenever we are shifting the dot position and we observe it a new non-terminal after the dot, then we should go and add the all production rules of the non-terminal from the original grammar production rules. So this is how I1 is derived from I0. So this is this one was dot E. When it is just added to I1, the dot position should be changed, and the similarly for E drives dot E plus T, we should change, and we should place it as E drives E dot plus T. Then I2 again can be derived from I0, because we just considered only the first two to generate I1. Next we can consider another grammar symbol after dot to generate new non-terminal. So when we are new item, sorry, to generate new item. So for generating item I2, we should consider the next items from which we can generate the new item I2. So since we have non-terminal T after dot in both production rules, we can just bring those two production rules to I2. So E drives T dot, then T drives T dot star F. So here what you have to keep in your mind is when we are adding the production rules having the same non-terminal after dot, this means we should consider only production rules having the same non-terminal after dot, or the same grammar symbols after dot, but not the production rules of the non-terminal after dot operator. So that's why we just excluded the T production rule, T drives dot F, in adding into I2, because here we are considering only production rules having the non-terminal symbol T after dot. Then I3 is derived from I0 again by shifting the position of dot after F, because this production rule is the only production rule having non-terminal F after dot. And I5 is again derived from I0. This is derived from I0 by applying go to of I0 comma opening bracket, and this I3 is derived by applying go to operation on I0, go to of I0 comma F. And this one is I2 is derived by applying go to operation on I0 then comma T. And this one is go to I1 is derived from I0 by applying go to of I0 comma E. So for I4 we are applying go to operation on I0, then the parameter is opening bracket. So here F drives in bracket E, but here bracket dot E, then closing bracket. Then what we have to keep in our mind is here, since we have non-terminal E after dot, we should add the two production rules of E from the original grammar, and again starting the dot placing dot operator from the left end. And because of this production rule, we should add the two production rules of T. Because of F, we should add the two production rules of F. Finished. So after this one, there is no need to add any more production rules. Then I5 I5 can be derived from I0 by applying go to of I0 comma ID, because we have ID after dot. And I6 now we finished generating items, another items or other items from I0. Now we should go for checking I1 if it is possible to generate another item from I1. From this item of I1 it is impossible to generate another item because this is a final item having dot on its right end. This already reached at the final position, so from this it is impossible to generate a new item. But from this item it is possible to generate new item. So I6 can be generated from I1 by applying the go to operation on I1, go to of I1 comma plus, because we have plus after dot. So this is E drives E plus dot T. Then since there is an internal T after dot, we should add two production rules of T from the original grammar. And again, since we have F after dot, we should add both production rules of F. Finished. So I6 can be generated from I1 this way, and I7 can be generated from I2. But here from I2 items, from this one cannot be used for generating new item because it is already a final item. But from this one we can generate a new item, so we can generate I7 from I2. So I2 comma go to of I2 comma star, we can generate I. Okay, so we can generate I7 from I2. So we can add the two production rules of F, and I7 can be I8 can be generated from I4, not from I3, because I3 already we have reached in I3 we have already reached the right end, so it is final item. It is impossible to generate new item from this item. Then we can now generate I8 from I4, so by changing the position of dot operator to after E. So after E we have dot. So since there is no, the grammar symbol is terminal symbol of symbol after dot, there is no need to add another production rule from the original grammar. But here since we are considering production rules having non-terminal E after dot, we should consider those two production rules into I8, not the production rules of E, but production rules having an internal E after dot. So the only production rules that should be added to I8 are the first two from I4. Then I9 can be generated from I4 here. No, not from I4, but I9 can be generated from I6. Why not from I4? Why not from I4? Because this one, if we are trying to generate an item from this one by shifting the position of dot after T, we will just reach at I2, an item which is similar to I2, which is already existed. So there is no need to generate new item from those two, because the item that we will be generating will be the same as I2. So that's why we just skip it, generating a new item from uh, go to of I4 comma T. What about this one? Go to of I4 comma F, because we have already had this item as I3, so there is no need to generate it as a new item. What if after go to, what if we apply go to of I4 comma opening bracket? It is referring to itself, it is referring to itself, so this is the same. So there is no need to generate it as a new item. What about this one? It will be just similar to I5. So go to of I4 comma ID will be the same as I5. That's why we are not generating any more item from I4. So I9 is generated from I6. That is go to of I6 comma T. So the only production rules are the first two, because the first two are having the non-terminal T after dot. So this is how we can generate I9 from I6, and I10 can be generated from I7. Why? Because this one cannot be used for generating new item, because it is already existed. I3 is existed as an item that can be generated from this, and this one is similar to an item generating that can be similar to I4, and this one is similar to I5. So I10 is generated from I7, so go to of I7 comma F, and I11 is just generated from I8. This one sorry, I7 go to of I7 comma opening bracket will be the same as I4. So there will be no any more item that can be added to that can be generated. So we have here 12 items from I0 to I11. From this one we cannot generate any more new item. From this one we cannot generate any item, because this one will be similar to I7. This one is a final item, this one is a final item, this one is final item. So from final item there is no need to generate a new item, because the dot operator is already reached the final position. So once we created this collection, this is what we call LR0 items collection. LR0 items collection. So this is just what represent this the go to operation, that is how other items are generated from the previously created items. So this shows or indicates the state diagram or transition diagram as a go to function. So once we created the LR0 items, those LR0 items, then we can follow this algorithm, simple algorithm for constructing SLR parsing table.